So now it's time to look at various ways of synchronizing the threads that we have been creating and made to work in work sharing constructs. The first construct we're going to look at is the barrier. We have seen earlier on the critical section and the atomic constructs. Those are ways to create mutual exclusion. Now we look at different kinds of synchronization primitives. So the barrier is a synchronization point where you make sure that all threads have reached the same point. So what it means is that each thread waits until all the other threads have arrived. And you can explicitly add a new barrier by the keyword pragma OMP barrier, like here. But in OpenMP there are also implicit barriers at certain points. First of all, as I mentioned earlier, is that there is an implicit barrier at the end of a parallel region. But there is also an implicit barrier at the end of work sharing construct like the for loop. So this is an implicit barrier for the work sharing construct constructed by the pragma OMP4 here. There is a way to remove that implicit barrier. Adding the keyword no wait here will remove the particular work sharing barrier at the end of this work sharing construct here. So here there is no barrier. And this might be useful at some times because in this case you show here there's some kind of big calculation where you use the ID to do some different work. Now if you don't really know how big this is and then you might want threads to go chunk on it as early as possible and therefore there is no meaning for the threads to wait here when they finished this for loop. So the first thread that finishes can still go on and do the calculation here. So the barrier, explicit by pragma OMP barrier, implicit in work sharing constructs unless you have specified the no wait keyword. The master construct is a way to declare or make a structured block be executed only by the master thread. So the master thread is the thread with thread ID 0. So this is the same thing if ID equals 0. That's the same thing as pragma OMP master. So the master thread will execute this, the others will not. There is no barrier here, so if you want if you need the other threads to wait for the master to finish, you need to explicitly insert a barrier like this. No synchronization implied. The single construct is sort of similar, but it's actually has different semantics and it actually belongs to work sharing construct. So the single construct, pragma OMP single, it denotes a structured block that comes after the single and which will be executed by the first thread to come to the pragma OMP single. And there is an implicit barrier here. So all threads wait for this single thread to finish executing this this code here, unless, as before, you specify no wait in case the implicit barrier goes away. Connected to the single construct or implemented similarly is the sections work sharing construct. So the single is actually the sections construct with only one section here. So in the sections construct, you specify pragma OMP section will tell you to have a structured block with sections, and then you identify each section with pragma OMP section. See the difference? S here and no S here. And then the first thread that comes here will take one of the sections and execute it. Second thread will take another one of the three sections and execute it, and so on. As usual with work sharing construct, there is by default a barrier here unless you write no wait clause here. This is useful to implement functional parallelism. If you have several functions that can be executed in any order, then this is a way to make the threads do different parts of the code. However, with the introduction of the task construct, which we'll be talking about later on, the use of sections has diminished greatly. The task construct is typically a better way of achieving the same thing. The ordered construct is a particular kind of construct to be able to order parts of a for loop as if it would be executed in the sequential order. It can be useful if you have I/O, for instance, and you want part of the code to be sort of doing an I/O operation in the same order as the sequential code. It can be useful if you have non-associative operations in reductions, for instance. If you have floating point operations and you need bitwise compliance with the sequential code, then the floating point operations have to be done in the same order as in the sequential code. Otherwise, the bitwise compliance will not hold. Floating point operations are not fully associative, even though the mathematical operation addition and subtraction is, or not subtraction but addition. Anyway, you specify that the for loop is ordered by giving the keyword ordered, and then you can specify the part of the for loop to be ordered. Because if the whole iteration is ordered, then it will be just sequentialized. So in this case, we assume that this one takes a long time, but this one code has to be ordered because we assume that we want to have a bitwise compliance on the result here. So this code here is assumed to be is specified to be ordered, and then the compiler will make sure it runs in the same order as the sequential code. So in addition to these sort of directives to synchronize and do work sharing, there are some lock routines that are less often used. We have functions to initialize locks, set locks, sunset, and test, and so on. And you can do this nested also. These are not that commonly used. You can do most of the stuff with the directives directly. I recommend that you go to the specification of OpenMP if you want to use these functions. Specification can be reached at the following website, www.openmp.org. So here is a wealth of information about OpenMP, including the specifications. Nevertheless, if you want to use the locks, this is how they use them. You declare a lock like this. This is quite similar to pthreads programming. You initialize it, you set the lock, and then you do your critical section, and you unset your lock, and then at the end you have to free up the storage when you're done. And so on. There are some other functions that are useful. We can set the number of threads to be used in the next in the next parallel region. So this has to be called before. I can't spell here. Before parallel region. This one inside parallel region. OpenMP get num threads will return the number of threads that are created. This is useful because most often you don't know that number from within the code you have, because this is set from the outside. OpenMP get thread num will return the ID of the code. OpenMP get max threads will return the maximum number of threads to be created. OMP in parallel is useful if you have code that is can be called from both parallel regions and from outside parallel regions. If you don't know if you are in a parallel region or not, this is useful. OMP set dynamic and get dynamic can be used to allow or disallow if the runtime system can vary in the number of threads from one parallel construct to another one. And then to find out how many processors you have in the system, OMP numprocs can be used. Again, there are a lot of other kind of routines that are less commonly used, and they can be you can read about them in the specification. So here is a way how to use these things. OMP set dynamic will disallow to 0 will disallow different number of parallel threads from one region to another one. OMP set num threads outside the parallel region, as you see here, will set the number of threads to create to the number of processors in the system, which is mostly the default in any case. Inside the parallel region, OMP get thread num gets the ID, and OMP get num threads will get the number of threads. And then there is some use of environment variables, and one of the most commonly ones is OMP num threads. So this is the way to control the number of threads that the program will use, that I usually use, and which is very, very convenient if you want to change the number of threads from one run to another one. So you set environment variable OMP num threads, and if you're running the bash shell on Linux, you just write export OMP underscore num underscore threads to say 4, and then next time you run the program, you will run it with 4 threads. If you have specified that the work sharing construct uses a scheduled runtime, then the program will look for the environment variable OMP schedule, where you can specify a schedule and a chunk size, and the schedule here is static, dynamic, or guided.